Hello, my name is Emma Kerr, and for my research project this summer, I worked on optimization of magnetic coil geometries for coherent control of electron spin states in organic semiconductor thin films under strong magnetic drive conditions. This was in Christoph Boehm's research group under the direction of the other listed co-authors in the Department of Physics and Astronomy, and I was a part of the SURP program this summer. As an introduction as to what our research group does is we study spin state transitions of electron charge carriers. So spin degree of freedom has been used for applications such as sensing or memory unit, but we basically need a way to read electronically what is going on in these electronic processes in a controlled way. So we build devices to observe spin state. So this is an example of one of our matchstick template designs. It is a bipolar injection device that is about 2 millimeters by 50 millimeters in size, and it is a way to manipulate spin in a controlled way. So we manipulate spin through our electrically detected magnetic resonance experiments, or EDMR experiments. As you can see in this center graph example, we can measure current running out of these devices and observe resonance. So our EDMR setup is as such. We have our device in the middle of this coil, which creates an oscillating magnetic field, which we called B1. Then we place it in a static magnetic field called B0. So what my research this summer has been concerned with is optimizing this B1 coil. I wanted to create a strong and homogeneous magnetic field across the entire sample area, as well as minimize impedance. Impedance is a function of geometry as well as frequency of the alternating current, and it is so important because we want to maximize electric current running through our coil geometry, as well as maximize energy transfer within our excitation circuit. So our excitation circuit is as follows. It is a 1-volt source connected to an amplifier, which runs current through our coil geometry. So what we were doing before is we were creating these geometries as shown in the picture on the right and doing some calculations by hand and then actually putting them into our excitation circuit. But what I did over the summer was use COMSOL Multiphysics, which is a finite element analysis solver and multiphysics simulation software, to actually simulate these geometries on the computer. So COMSOL allows you to assign certain boundary conditions to these unique geometries. So I made these geometries out of copper. I applied 1 amp of current and a frequency of 100 megahertz to each of the geometries, and then I measured the magnetic field that each of them generated, as well as the impedance across the entire domain of the structure. This allowed for more accurate calculations of magnetic field and impedance, as we don't have to make certain assumptions or simplifications that we would have to do if we were calculating these by hand. So here are the 7 significant coil-like and non-coil-like geometries that I simulated on COMSOL Multiphysics. Here's an example of one of the results that I got. This is a single loop turn result. A single loop turn is something that you can commonly see in an E&M textbook, and I simulated it on COMSOL Multiphysics. So the big color plot picture is a plot of the magnetic field strength in a 3D plot, and then the green and red lines are the cut plane lines of the X and Y axes, where I measured the magnetic field strength going along those lines. So that's what the plot in the center is. And as we can see, we find the highest magnetic field strength across both axes in the very middle of the coil, which is exactly what we'd expect, and this is about the strength that we'd expect. I simulated this as well as my 6 other geometries, and you can see the full results on my poster, so go check that out if you want to see the specifics of the homogeneities and the magnetic field strength, as well as the impedance for each structure. This data suggests that we should try implementing a split ring coil geometry into our experimental setup, as it provides the most homogeneous magnetic field across the entire sample area, which is something we haven't tried before. However, this data also suggests that we have pretty much already maximized our magnetic field strength that we can use with our experimental setup that we have currently, and the given parameters that we already use. So in order to maximize the magnetic field and increase the magnetic field strength, we would need a separate design, which I go into more depth in my discussion. So please check out the rest of my poster to see my future exploration and my discussion, as well as the specifics in my experiment. Thank you so much, and I hope you guys can check out my poster.